Okay, you're really sharp on time. So thank you for coming for the last lecture of this course on symmetry and topologies. Okay, so we'll see what we can cover today. I should apologize in advance that I will not be able to describe so many applications of all of this formalism. I will mention a few, but then I think that, well, in retrospect, I can say that the purpose of these lectures was to explain the fundamental technical tools to be able to understand all these diagrams that people draw, and today we'll see some more algebraic structure. And well, and then in principle, if you follow this, then it should be very easy to follow what is described in the recent papers and literature and talks and so on. So, but okay, so today I want to at least answer this question that I outlined last time. So let's just remember what the past episodes told you. That we have generalized the notion of symmetry bit after bit, and now we have reached this definition, which is summarized by these two equivalent statements. If you have a higher form symmetry G P, then it means equivalently that you can couple the theory to some background gauge field, which is a P+1 form, and which is invariant or almost invariant under background gauge transformation. And it's almost because now we allow for this phase, which is a tooth anomaly. So I should write tooth anomaly. And in the dual description, in terms of symmetry defects, they are still topological, but then when they are merged together, they satisfy the group law up to a phase. So that's the addition of last time, the anomaly. And in the 2 weeks ago, we discussed at length that if we have a non-anomalous symmetry, then we can gauge it. It's a consistent operation that takes a theory and returns another theory, where the symmetry that you gauge is gone, so it's no longer a symmetry. You might have some other symmetry, but okay, so that was a cost. And now, putting these two things together, we have this very natural question. If we have a group, a symmetry group, which is anomalous, but it has a subgroup which is non-anomalous, what does it mean? Well, you can describe it by either of these two descriptions, but for instance, you can say it here, that if when G and G prime are in the subgroup H, then the phase is trivial, then it means that the subgroup is non-anomalous. So if you have such a situation, there is a thing that you can do. You can gauge it. You can pretend you don't know G, you gauge H, and now the question is, what is the remaining symmetry? And in general, that's a very complicated question, which has a complicated answer, and that I would like to answer in a particular case, which is when G is a product. And already there, we will see that even though G is a product, there is a very rich answer, which covers what's known as higher group symmetries and non-invertible symmetries. So that's the plan for today. So again, I will not answer this general question, but I will answer it in the case where G is U1 times U1. So that's almost the simplest case. And then I will assume that one of the two U1 is non-anomalous, so I can gauge it. But then there is G by itself is anomalous. And so we want to see how the G anomaly will pervade the resulting theory after gauging. And we will see that this forces us to have an extended notion of what symmetries are in at least two aspects. So for this, I want to also summarize some of the things I said at the end of last time about the anomaly. And so I think it was in the first or second lecture, we saw that, so yeah, this, like the first part is back on some more words on the anomaly. So if you have a symmetry, then there is this ability to couple to background gauge field, or there is this existence of operators, and you can put this together by saying that the theory can be coupled to a foam of topological defects. And if you want to gauge, for instance, that means that you insert all possible such forms of defects. So there is a so this is in 2 dimensions. You can imagine these are all topological defects. And so this thing, on each edge, you can put a group element, G1, G2, and so on, and that defines some kind of background for your symmetry. And okay, that's you can start from the configuration where you don't have this, and then a certain lambda will create this for you. And then when you gauge, it means that you sum over all topologically distinct insertions of things like that. And then, yeah, I think it was in the first or second lecture, we discussed a little bit the axioms that this foam has to satisfy. And there was one which was particularly innocent looking, but then we had actually some comments about it, which was if you have something like this, then so that contributes with certain element, which is G1, and then maybe there's G2 here, and G3. Then at each junction, you should have the G's matching up. So this is here, there's G1, G2. And now here there is G1, G2, G3. But then there is a deformation of that, which goes to this kind of diagram. So same level, 1, 2, 3. But now here there is 2, 3, and here there's 1, 2, 3. And so one of the axioms was that the insertion of this or the insertion of this gives the same. But then I mentioned already at the time that this was actually if there is no anomaly. So if there is an anomaly, then the anomaly will be associated to what happens when you go from here to here. There is actually this is equal to that up to some place times e to the I something. That's the anomaly. And this equation, yeah, that's the analog in a way of the one that we discussed last time in quantum mechanics for the anomaly. So I want to say that all these things are in the same class. These are kind of generalized associativity. So let me explain why this is associativity. So first, let me. So this is what I said several weeks ago, and now just at the end of last time, we were discussing quantum mechanics. So in quantum mechanics means d equal to 1. So you have all these things, but in d equal 1. So when d equal to 1, so quantum mechanics, then what is the network of what is this form? Well, it's just a collection of points. We have a collection of points. And what is the only topologically non-trivial operation you can have a collection of points like this is to merge 2 points. Let me actually just do 2 points. One here, one here. Let's ignore the other ones. And another configuration can be the one where the 2 points are merged. So this was G, H, and GH can merge into DH. And what we said last time is that under this process of going from here to here, there can be a phase, and that would be the anomaly. And that was so here the like this is equal to this times e to the I omega G and H. And then what we said is that this means that the group G acts projectively. If you imagine that here the states G and then H acts, and here GH acts, but then there is a phase. So this was in connection with projective representation. And we also discussed that this was associated to the second group cohomology H2 of G with values in R mod 2 Right, so that was the d equal 1. And at the very end, I argued that the fact that the partition function here or here is a complex number up to a phase. This can be, what is the complex number up to a phase? It's the same as a vector, a complex number up to a phase is the same as a vector in a one-dimensional Hilbert space up to a choice of normalized basis. Right, if you have a one-dimensional Hilbert space, one-dimensional complex space, then you can pick a basis. If it's normalized basis, it's length 1, but then there is a phase ambiguity. And then when you have a vector, you express it in that basis. So you find the coefficient, and you find exactly that complex number 2. And so that led to the idea that one way to understand geometrically this phase was to say, actually, my one-dimensional theory here, quantum mechanics, is just some edge theories of a one higher dimensional theory, which is a topological theory and whose space of states is one-dimensional. So it's an invertible topological theory. D-dimensional theory equals 1, but now let me generalize to D. So D-dimensional theory with anomaly can be interpreted as, we interpret as the boundary of D plus 1 dimensional topological quantum field theory, which is invertible here. So invertible means that the space of state is one-dimensional. And I remind you that if you have a QFT, the space of state is associated to a codimension 1 subspace of D, and so codimension 1 is D plus 1, it's D-dimensional. So you have a one-dimensional. What is the space of state? What is the space of all possible partition functions? And that's exactly reproduces the anomaly. So the picture, right? So then in picture, at the very end, right? So we have, this is D equal 1. This is the whole space of QFT, and then we have the operator G, the operator H, and then what I say is that we should consider this as the boundary of some two-dimensional theory. So here is the topological field theory, and then what should it be? What should the action be? It should be something such that if I have this, it should be equal to this, with no phase. The phase will be absorbed. So how do I do this? Well, I just say there is a topological move, which is this. So here, within the two-dimensional theory, you see I kind of add a dimension in which I implement the associativity, the function here. So G and H become GH, and then here there is just GH and nothing. And I want to say that the partition function for this is the same as for this. And so what should I do? Well, I say that the partition function, there is a component due to the boundary, let's put in green, and then the component here is Z. And here the partition function associated to this is Z times e to the I omega. If I want this to be equal, then I should say that the orange part contributes e to the I omega. And so this phase should be associated to this junction that is in the bucket. So that's the idea. You see, it's just a matter of transferring the equation which was an anomaly before was just because we forgot about the two-dimensional thing. If we add it back, then there is no anomaly. It's just some standard topological move. So I will say a bit more what kind of theory gives that, but let's just draw one higher dimensional thing. So this was the d equal 1 case. Let's draw the same in d equal 2. So now the boundary is two-dimensional. That's the boundary. And now, what is the equivalent of this this junction problem? Now, if I'm in 2 dimensions, the analog is actually what I started drawing here at the beginning. And that's why it's a generalized associativity problem. So here we can draw a diagram like this. So here we have G, H, K. They merge a G with H and then with K. And they give here GHK. And then the other possibility would be to do first H with K and then they merge with G. And so how would this be done? Well, there's now a 3-dimensional theorem here in which these extend as surfaces like that, and that as well. So at the end there's the same diagram. This. But now H goes from the left to the right. I hope it's clear. So here you have this tree with the leg on the left, and along this evolution, it evolves and goes like this. So here there is something happening. You see here there was a point where something was happening. Here there is this point where something is happening. And now the anomaly, but then I should draw the other one here. Same picture. This side is now just this with trivial, everything trivial. So you see from here to here, we have kind of pushed this whole configuration on the boundary, and it has implemented this change GHK to GHK, but with the other. And now I can draw the same equation. The partition function is Z, and then it's equal to Z with a phase I omega GHK. And so the contribution of that point should be like this. So that's the anomaly. Yeah. And so the anomaly in D dimension involves T plus 1 elements of G. Here omega involves 2 elements, G and H. And here omega involves 3. And when we were in D dimension, it would involve T plus 1. That is scalar harmonics. Okay, so now just one comment. I will not spend too much time discussing the TQFT, but in this particular example, the TQFT can be described quite explicitly by just a state sum. So I think maybe I should assume that G is finite. is finite. Maybe a billion to have a problem with signs, but actually these are not very important things we can generalize. Then there is we can actually define what is this orange thing. This orange thing is just called the Dijkgraaf-Witten theory. So what is the Dijkgraaf-Witten? Evaluated on some manifold, equal to n of dimension 3 plus 1. So n is here is this, and 2, here is the Waltonian, and 3 is the d plus 1 dimensional thing. What's the partition function evaluated on this? It's just a state sum. So you have a prefactor, the order of G. So basically, what you do, you take a triangulation, which will be the dual triangulation to the orange words here. So maybe I pick another color, red, no, blue. Blue. So you see there is a dual triangulation here. In this one, I hope that you see that the triangulation is a tetrahedron around this point. There is 1, 2, 3, 4, 5, 6 planes meeting at this point, and it's a bit easier. Let me draw this from a slightly different perspective. Just wanted to see that it's a tetrahedron. Like this diagram here, you know, the orange on the left, it's exactly what I drew here. Actually. You see, this is kind of an S channel, and the other one is a P channel. So I can draw this as this on one side, and this on the other side. Then the dual is just this, and here it's just this. And now when I go from here to here, and I evolve, it's basically this diagonal shrinking and then opening again. None of the other four edges change. So actually what you've done when you glue all of this, you glue that with that and so on, and then you end up with a labeled by G, A, H, K, and then you have here you have H, K, and so on. H, and back you have the product of the three. So this picture is the dual to the orange picture here. And then you should just, so you triangulate your space. So in order to compute this, you pick a triangulation. And then let's do it in 2 dimensions. You pick a triangulation. Then to each edge, you associate a group element, G1, G2, and so on, G3. Then you should have it in a consistent way. So whenever you have a triangle like this, G1, G2, G3, you should impose that the product is 1, which is the conservation of the group element functions. So yeah, you do this and then you just sum. So here you have once you have the triangulation, okay, minus the number of vertices, then you have the sum over flat labels. Flat labels just means you label the thing and it should be flat. So it is the curvature condition. Product is always 1 on each cell. Sum of flat labels, and then you sum over all the simplices. And what do you sum? You sum some prefactor, which is basically omega of S. So basically basically what I've written here. Here we had only one. We had a very trivial triangulation, which had only one triangle, one non-trivial triangle, and then all the rest is trivial. And then on this triangle, you sum omega. So omega it takes two walls, G and H, and it outputs a number. Here it's a tetrahedron, so you need 3. And so basically that formula just is the general thing. And the point is, this is a well-defined thing. It can take any d-dimensional manifold with any topology, any group G, and this outputs a number. So this is the partition function. Now, if you want to have states, now you fix a boundary condition, like here. You say on the wall, I impose that I have G and H, so that's fixed. So those guys are fixed, G and H. And now you do the same. You sum over all triangulations, which have G and H fixed, and you compute again. So this is called the Dijkgraaf-Witten theory, and it exactly absorbs the anomaly.
Juste peut-être pour me vanter peut-être un peu, mais at the same time as Dijkgraaf-Witten, we came to the same theory from the quantum group point of view.
Maybe you should call it the...
No, okay. So it's the double but yeah, aussi Dijkgraaf is also an author.
Yeah, so okay, that's the standard name, but as always, the paternity of the theory. Okay, so yeah. So yeah, so that's just to show that it's explicit. Now, in the case that I will be looking at, we actually don't need to know so much. There is another way in which we can encode what the anomaly theory is, and it's using anomaly polynomials. And when we are in the continuous, so here this works for any group, in particular discrete groups. If we are in, we want to deal with U1, because the goal is to do something like the standard model or QED at the end. So for this, it's actually a bit simpler to work with polynomials, and I will just show you in the case that, if you remember, we started from the compact scalar in the dimensions. That's why we arrived here and here, actually. So when we have the compact scalar, so now let me say anomaly, so now anomaly polynomial. That will make all of this very concrete. So in the d-dimensional compact scalar, so remember the action was some number 1/2. Let's not put the integral over d-dimensional of u phi.
Just to be sure, in 3 dimensions you had H2, but in higher dimension it will go to Hn. I mean,
it's Hd plus 1. Sorry, I didn't write. For d equal 1, it's H2. For d equal 3, for 2, it's 3. And yeah, in general,
H3 is related.
yes.
It's not. If you have finished to answer to Vincent.
Yes.
I have another question. That Dijkgraaf-Witten partition function should give a phase A to E omega. I don't see it.
Yes. Oh, sorry. Okay, this is the phase. So if I write it in additive form, that's the phase. So you should take exponential for all this. Just the way I've written it is omega is in U1, so it's already a phase, and then I should maybe do a product here.
Okay, that omega is not the other one on your left.
Yeah, okay, I agree. Because I keep changing between R mod 2 pi z and okay, let's do the sum here.
It's exponential of or something like that.
And then we take the exponential. Yeah. Just confused about this. Yeah.
And there should be some I also, no?
Well, the tetrahedra is a phase, and then you take the product of the phases.
Yeah, that's the idea. You have a. It's basically what is here. So you have a. I'm just confused about the sum over the labelings. If it's within the sum, or I think yeah. But okay, it's clearly if you write it this way, then if you have many triangles, you make the product of all this, so that the omegas are added. Then you take the exponential. Maybe. I hope it's covered.
Yeah, and also the sum, the first sum is a product.
Well, that's the. I'm not sure. I should check. I can give an. But we have to sum over all the labelings if the topology is not trivial. Okay, I can give a.
No, but okay, at least now I see a phase.
An exercise is if you have if G, so let's take an example. If G is Z2, Z2, last time we discussed, this is the simplest group which has an anomaly, so it has H2 of G with value in U1 is Z2 again. So here there is a non-trivial element of that. And if you evaluate Z, so Z of course depends on this omega that we picked, so let's put Z omega. And then this is I have to put here a two-dimensional thing, so let's put a Riemann surface of genus G, sigma G. That means Riemann surface of genus G. Then that's an exercise. You find 2 to the 4G minus 2 if omega is the trivial one, and you find 2 to the 2G minus 2 if omega is minus 1. Now with this, it should be enough to.
Just to say why 3, because a tetrahedron is a 6J symbol, in fact.
Yeah, sure. So in
special, I mean,
when D is 2, then indeed these are the 6J symbols. But in
higher dimension.
In higher, but you can also, well, here for instance it's lower. So this is two-dimensional, so this is not 6, this is just some cycle. So you can try to. Any other question on that? Anyway, this is I will bypass this. I just wanted to mention because I started with this last time, but I will kind of bypass by using the anomaly polynomial. So in the compact scalar, we have discussed already basically every time I've mentioned this example. We have a U1 momentum, which is a zero-form symmetry, and we have a U1 winding, which is a D-2 form symmetry. And then we have seen last time that there is an anomaly, a mixed anomaly in here, and we computed it, and it gave, yeah, so there was an anomaly, so what I erased now, but what I called A was 1 over 4 pi squared dB and the lambda winding. So last time we wrote exactly this formula, which just comes from, we wrote the action, we coupled it to background gauge field, and then we saw there is no way to make this independent of all the background gauge transformations. And then with one particular choice of counter terms, A was written in this way. So there is the B momentum here, which mixes with lambda winding. And now from the perspective, so this A is what is in the exponent of the anomaly. So the anomaly is that D of, I write B for the genetic of both these, because D lambda is Z of B times e to the a, e to the I. That was what we compute. Pre-series is very easy to compute everything. The prefactor should be correct. So that's what we got. And now, since I'm saying that this should be interpreted as a one higher dimensional action, I can easily write that A, there is an integral missing, integral over, and now I'm just saying that A is integral over the one higher dimensional thing, n, b plus 1, of, so I have to find what this is the d of, and find that this is the integral of delta. So this is d, I still put the boundary. So this is still the same thing as here. And this thing, I say this is the delta of b. This is b and 1, where delta, this is the variation of b winding. B winding, b minus 1. Right. Okay, so that's so now the thing without the delta, I call it the d plus 1, the degree d plus 1 anomaly polynomial. And, so that thing, definition is delta of a polynomial I of degree d plus 1. See where we are in the anomaly theory. And now these are the descent equations for those who know. So we started from I t. The initial anomaly was the integration of that thing. What 1 over 4 pi squared d d 1 d lambda. So here, importantly, the phase depends on the n lambda. But then we could write this as these are the descent equations here. But g I is delta of something of degree 1 plus 1, d plus 1. That's what we do here. So then when we go to the one more dimension, we are dealing with that one, with I d plus 1 equal, so we recognize that this is the variation of b. So let's get this. b is 1 b winding minus 1. This. And then, so now we have this integral of the variation. So the integral of the variation is equivalent to saying we can pick two slightly different ends, this n3, we can take two slightly different ones, and then the full anomaly is the integral over what is in between, which is yet one more dimensional. And here it's we just define I plus 2 is d of that one, which is just now that's a d plus 2 form, and we can write the anomaly as with this equation. So the d is at the 1 over 5 in it, not the integral. And then we're running all these equations, so we have this equation. These are the descent equations. This one and this one. So generally, if A is that, then we can write the anomaly as the integral of d plus 2 dimensional manifold of this I d plus 2. So these are, again, slightly formal manipulation. The point is now, this thing depends, or this thing depends only on B, not on D lambda. The dependence on D lambda is hidden in the boundary. So the conclusion of all this, I just wanted to arrive at this simple thing, and then we can explain the effect of gauging. Conclusion of all this, let me summarize here. In the case of the symmetry, which is U1, the product of U1s, so this is the summary of this discussion, which is maybe a bit fun. That's the only thing we will really use. So summary, there are 2 points. The anomaly of zero-form symmetry in V dimensions is stored, can be described equivalently as an element omega in HT plus 1 of G to 1, or equivalently in a polynomial of D with D plus 2, polynomial in B, in the background gauge field. And the explicit one that we need is if G is a product of U1s, it's just a product of U1 symmetries over some, we have n U1s. Then this anomaly polynomial is, so each U1 has a B1, and then it's basically exactly this. We can believe that this will generalize. Here we found DB wedge DB for the 2 different B's. In general, you can have all the products of these. So this I is a sum over all the indices I1 from 1 to n. How many I should we put? Well, we need to have degree D plus 2 in total, and each dB will contribute 2. So we need D plus 2 over 2. So we select D plus 2 over 2 groups in here. And then we have a constant, which is the anomaly constant now, which is kappa, I1, D plus 2 over 2, times dB, I1, so this is a long formula. It just tells you that if you have a product of U1s, the anomaly is entirely contained. So if you have just one U1, okay, this is what we said here, it's in the HD, and that's Z, so the anomaly is an integer. If you have many U1s, it's many integers. But where are the integers? These are the anomaly coefficients. These are the anomaly coefficients. So the anomaly is you should give all these numbers.
There are concrete expressions.
There are.
Concrete expressions.
Yeah, there are concrete expressions depending on your theory. This is very general, so you need to describe what are these things. So let me give some example. It will become very concrete. At the end, the goal is to do QEDs. Very concrete.
Would it help to compute these omegas in the case of the finite groups? It's the same. I mean, you compute.
Yeah. It's the same. But okay, here, so if G is U1, then H, okay, we should specify which one. So last time I gave what is H equals 1 of U1. It's 0 or U1, depending on if it's odd or even. So it's easy in that case. So let's actually now, from now on until the end, we will focus on a particular case. So from now on, let's pick D equal to 4. We want to do 4-dimensional QFT. And let's pick the symmetry to be U1 times U1, 0, 0. So we pick a theory which is 4-dimensional and which has 2 U1 symmetries. They are both zero-form symmetries. So can you give me an example of a theory which has this? Yeah, so for instance, typically free fermions, they will typically have this. There is the U1 which rotates the phase, and there is the axiom U1. So that's typically the thing. So yes, with gamma phi. And so what we're going to do is let's do this. So we take a bunch of free fermions. They have this degree of freedom, and then we want to gauge one of them. If we gauge one of them, we end up with QED because we had before a U1 symmetry. Now it's gauged. It's no longer there. That's a gauged redundancy, and we still have, for instance, the axial symmetry. Or if we have a bunch of fermions, we will have maybe an SUN favor symmetry as well. So there could be some other factor. But okay, these are the things that are in the standard model all over the place. So this structure is really, really common. So I'm doing it in a bit of an abstract language, but this is the thing. So what we want to do, which I erased, the question that I asked at the beginning is exactly that. You start from a theory, you write a Lagrangian, and then you want to say that one of the U1 is actually gauged. You gauge it. So first you need to check that it has no anomaly. Otherwise you cannot gauge it. But if it has no anomaly, well, maybe there was a mixed anomaly between the two. And the question is, what becomes of the other one if there was a mixed anomaly? So let's see. And now we can exactly quantify how much anomaly there was. We just have to write this with d equals 4, so that's 6. And 6, so in each term of the polynomial, there will be 3 terms. So this is why anomalies are computed in, if you have fermions, you compute triangle diagrams. If you're in 10 dimensions and you do string theory, then D is 10, then this is 6. So you compute hexagon diagrams. As we discussed last time, chiral fermions are one possible source of the anomaly, so they must come from such a thing. Of course, these are not needed. There are other sources of anomalies, but if you have chiral fermions, then you know that the anomaly will come from computing one loop diagrams with how many edges? D plus 2 over 2. So in particular, so let's do it for this particular case where we have 2 U1s. Let's give them names. So this one I will call A, and this one, for some reason, I call it C. Just I need to distinguish them. One is called A, one is called C, and so that means that the associated background gauge field I will denote by A, and this one I will denote by C. These are 1 terms. These are the background gauge fields. And now all the anomaly content is contained in an anomaly polynomial, which is I6, which is 1 over 2 pi 3. And then I have how many terms? 4 terms. All possible ways to put 3 things together in a symmetric way. So let's write all the 4 terms. So there is a term which is kappa A. I divide by 6 just because of here you could of course put some numerical factor in the way to define those. So I will define it this way. And then you have DA1, DA1. Then there is AAC, DAC. Then there is ACC. Here it is to like this. And then there is CCC. Okay, that's it. So the statement from the previous analysis or from whatever perspective you like, in the end, when you have U1 times U1, the anomaly is contained in 4 numbers. These 4 numbers. How do we compute them? Well, if we have a bunch of fermions, then you can just, those things, they are just coming from the one loop diagrams. They are just the sum of the powers of the charges given by those. So for instance, like this term is the sum of the QA, QA, QC. So each fermion has a charge under each of the 2 groups, and then you sum those.
From the abstract point of view, do you have any expectation on the value of k? I mean, should they be rational or real?
Right. Yeah.
Or
yes. So from here, they should be integer if you put the right normalization. And actually, that's why here I didn't want to mess up. But you could put the factorials and so on. But here they are all integers. That's why I put this normalization.
Okay. Fine.
So you can interpret these polynomials in terms of Chern classes and so on. But,
okay.
But yeah, and then that's how you would compute them. So for instance, in the standard model, so let me first say one thing. We want to gauge this one. That's the goal. We want to gauge that one. But this is what I promised. I promised you I would take a group which is U1 times U1 and I would gauge it. And the question is what remains. So if we want to gauge it, it would rather have no anomaly. No anomaly means that guy here should be 0. So in the standard model, of course, this is satisfied. If you take the U1 of a hypercharge and then you sum the cube of all the hypercharges over all the fermions, you find 0. Otherwise, it would be inconsistent to gauge that. So just put that. So we assume that this is 0. So I just assume that. So now we're left with 3 buttons to play with in our understanding of what happens after we gauge. This one here, AAA, this will be the anomaly, the 't Hooft anomaly of U1A, and okay, this will remain what it is. There is not so much to discuss, so we can keep it along for the ride, but then since it will tag along for all the formulas, I will just also assume it's not there, just for convenience. So this would be the 't Hooft anomaly. And I will assume it's not there. And then we have 2 more. So 2 more, and these are the ones which will interest me. There's this one. This one will have an effect. It will completely change the structure of what symmetries are, and this will be the first time that we will have to go beyond groups. So this one will lead to higher groups. Actually, in this case, 2 groups. So this is what I will discuss now in the second part of today. And then the last one, this one, also has an effect, and this is what leads to non-invertible symmetries. And but it had a name before it was realized that it would lead to non-invertible symmetries, and the name of that particular coefficient in the anomaly is called the ABJ anomaly. It's called ABJ if you interpret this guy as the axial symmetry and the other one as the. So this one is the axial global symmetry and that one as a gauge symmetry. So the goal is now, in the time that I have left, to discuss in turn this and this. And sometimes, okay, I will just draw it here next to it. It's good to keep in mind how you would compute those things. If you had charged chiral fermions, you would compute triangle diagrams. And in a way, that one you would compute by doing a triangle of AAA. A is the global symmetry, so it would be global, global, global. That would be at top. The higher group would come from a diagram where you have two global and one gauge current. That one is the opposite, one global and two gauge, and that one is the would-be gauge anomaly if it was there. But then it would be inconsistent to gauge. That's kind of the classification of anomalies for a product of two U1s in 4 dimensions. If you want to do it in 6 dimensions, then you will have squares and you will have one more type. You could also put not 0 form, but 1 form, and then okay, you have to compute if you have 2 1 forms in 4 dimensions, then that thing would be of degree 3, and you can put 2 of them together, so you can have a mixed anomaly and so on. So there is infinite variation from now on, and for concreteness, I will focus on this, which is the closest to reality. Is the setup clear? So now our question has become more concrete and more precise. We have this global symmetry. We assume that that one is 0, so we can gauge C. So we do gauge C. And we assume that the others are also 0. We keep only the blue one. And we want to know what is the symmetry of the resulting field after gauging. And so I already get the answer. The answer will be higher group. In this case, will be part 2. Yes. Yeah. So if D is odd, and if you have only U1s, you cannot write a polynomial with only DDs. So there is no anomaly. But of course, if you have a U1 0 form and a 1 form symmetry, then you can have an anomaly. So that's why typically when people don't discuss higher form and so on, they would say that in odd dimension it's non-zero. Okay, so let's look at this case. So again, here I'm assuming that K AAC is non-zero and all other are 0. So if I do this, then well, from the way that I constructed these polynomials, I was a bit fast, but you can undo all the construction and see that this the polynomial here is reflected in the conservation of the current. So naively, or no, even non-naively, we have a current. We have a current for the A symmetry, which is J, the 1 form A, and then the conservation is DJ, D star J is there is this factor 1/4 pi. Doesn't matter. And then there's this constant K. Two. E, D, A. So if you translate back to current as we had at the beginning, this is the equation. So the current for JA is not conserved. The whole point at the beginning was that we had a conserved current, and then from there we could build topological operators. And now we cannot do this because it's not conserved. In particular, it's very important to notice that here, this term here is now a dynamical. It's dynamical. Now it is the field strength of the proton. Because now U1C is gauged. So you cannot just say, this is the counter term and I will remove it. You cannot really do that. So what do you do with that? Well, let's try to write how the partition function transforms. Now I'm literally just plugging this I into the formula that I wrote before with the I's. So I said that Z so I can couple it to background gauge field. So let's say before gauging, this was the situation. And then C. So before gauging, we had the two U1s. I can put a background gauge transformation for both of them. And then I have the anomaly of 3 the I over 4 pi squared integral over M4, now in 4 dimensions, of the coefficient AAC over 2 lambda A dA GC. This is the anomaly. This is basically, I'm just saying that take the anomaly. And then importantly, if you have the lambda, see basically, if you remember the descent procedure, the lambda was replaced when you go 2 dimensions higher by a dA. So now you undo this, so dA becomes lambda, and then you still have the dA dc. So this is the anomaly coefficient. So yeah, so what do we do with this? Well, there will be a trick that allows us to still have a symmetry. So the goal is to construct a topological. And the trick is to do the following. You might be wondering why I call them A and C. It's because there will be a U1B in between. When we gauge, when U1C 0 is gauged, this is what we discussed in the third lecture. We discussed gauge theory and so on, and we saw that there was central symmetry and there was the magnetic symmetry, which was emerging, and these were one-form symmetry. So here, let's focus on the magnetic symmetry, under which nothing is charged. If we want to do, so remember, we want to do QED. So in QED, the electric one-form symmetry is broken by the presence of the electrons, but the magnetic one is unbroken. So that one survives. So when UNT is gauged, there appears a magnetic U1, now I call it D. It's a one-form symmetry. Magnetic U1D. What does it mean? It means that there is a current, a two-form current, JB, which is just I over 2 pi. This is what we wrote also in the second lecture. Of DC. It's convenient that C is called C because you cannot really distinguish if I wrote an uppercase or lowercase. But now, with my convention, C is now lowercase because now it's gauged, it's a dynamical. So now there is a dynamical C, but now this thing is conserved. This is the magnetic two-form current. And so there is a background gauge field, which is B2, and the coupling with B2 is the usual thing. And so the coupling with B2, which is the background gauge field for the symmetry. So now there is no longer a C. This we cannot use anymore. Now there is this one that we can use. And the coupling with B is given by the same formula that we had several times, I over 2 pi, integral of D2, wedge D, D1. Just D2, wedge the star of this, which is star. So this is the coupling with D2. And now, if you stare at this coupling, and if you stare at the problem that we had here with the anomaly, you can see that a solution emerges. So let me write it. Um, so if we prescribe the background gauge transformation as follows. So now A equals to A plus D lambda A 0. So this one we don't change, it's the same as here. But now B, we just prescribe a new kind of background gauge transformation, which is B plus its coefficient, which is the one form, and plus, very importantly, some coefficient kappa, by 2 pi, lambda A 0. So we prescribe this, and here I set kappa, this thing. You are free to adjust it. That's what we can play with that. And then if you look at the coefficients here and the coupling, which is here, you see that I can absorb this term by a transformation of this term, provided B transformed in the right way, because it's wedged with EC and it's wedged with EC as well. There's the lambda will come here, so that term here is that term here. And kappa has to be equal to minus 1/2 of kappa AAC. So if I fix kappa to be that number, now I have those background gauge information, and now the theory is invariant under background gauge transformations. So even though here it seemed not possible, because if I shift by lambda A, it should still be allowed, and here it's manifestly not the case, because I have this shift by something that depends on dynamical fields. This is what you asked last time, that I cannot put any phase, cannot depend on dynamical fields. But actually, if I prescribe that B transforms in this way, then the theory is actually invariant. So this is the law that you can prescribe. So the price to pay is that the transformation of B now involves A, which means so we can look at the consequences of this from various point of view, but the most striking one is so even if B2 equals 0 and lambda B2, lambda B1 equals 0, so I start with no, I don't, let's pretend I'm in this theory, so in QED, and let's pretend I forgot that there is a B. I don't want to think about this. I just know that there is my U1A symmetry. Well, this tells me that this would be incompatible to forget about this, because if I shift A, so if I activate some background A, and I shift by a dA, then B becomes non-zero. Even if B was 0, lambda B is 0, this term would not be 0. Even if B is 0 and B2 can be activated by a background gauge transformation. So that means that A cannot live by itself. So that's the consequence of the anomaly. Because there was a mixed anomaly, after we have gauged this one is still it's a good symmetry, maybe it's anomalous, but it's not really a group, because if I remember that this emulates the composition, the group law. So this is just not really a group. At some point, if I multiply two elements, I just don't get something in A. I need to involve something. We will try to see what. Are you tired, or should I do 10 more minutes on break? Yes, okay. So let's have the break. So after the break, I will explain, is this a group or not a group, or what is it exactly? But you can guess soon. Okay, so let's have a 10-minute break. So yeah, so the goal is to try now to explain what are the physical and structural consequences of this background gauge transformation. I kind of have to make a choice now because in view of time, I will probably say very, very little about the non-invertible thing, but I found it relatively difficult to write clearly why this is a two group and so on. So maybe I should just do this and we can discuss the other things later. Yeah, so the first thing is, where should I start? Yeah, so okay, let me first write one more equation here, which is the field strength. Well, okay, no, we won't need the field strength. So let me just write the conclusion that we draw from this little part. We started from a theory with a U1 A times U1 symmetry. We have a theory with this symmetry. And we had a mixed anomaly KAAC non-zero. And then the conclusion is if we gauge U1 C, so of course when I say this is non-zero, I assume that all the others are zero. So because CCC is zero, I can gauge it, and I obtain another theory with some other symmetry structure. For the moment, my only vocabulary to describe the symmetry structure is this orange box here. But as we have seen throughout these lectures, if we know background gauge field transformations, we should be able to also write symmetry defects, how they merge and so on, and also the algebraic structure. For the moment, algebraic structure was always just groups, so I did not really emphasize it. But here it will be not a group. So let's see what it is. So first let's give it a name. So the name will be U1 A, still there, times U1 B, the new symmetry that has arrived, which is given by this. It's a one-form symmetry, but now it's not just a times. It's a times with a kappa. The kappa, you should think of it as a kind of structure constant. It's something that will make this non-abelian. So it's a bit like a structure constant in Lie algebras. So kappa, as we know, is erase it, but it's basically it comes from an anomaly of U1s, and so it is a quantized number. So kappa is actually an integer. A bit like structure constants, they have some integrality properties. So this is integer, and then just to complete the circle, if I gauge U1 B, I go back here. I will not really describe this, but that's to say that no information was lost, and it's really gauging is a change of description, but the content doesn't change, but no information is lost. So I write this, so I write this times with a k, with a kappa, and this I claim is a two group. And I would like to just describe what a two group is and yeah, to be a bit more explicit here. And also we should describe what are the symmetry defects. So the most naive thing we can do is let's try to describe symmetry defects. So to write symmetry defects, it's useful to go back to the conserved currents. So let me write the conserved currents. So we have D star very A, which is, that's another thing that we can compute again from this formalism, combining these equations. Now, this star A is not constant. This is where we start from. It's here. With the right constant, so now it becomes plus minus. Just don't trust the sign too much. Also box, also important one. So you see, we have these two boxes are actually nice to compare. From this one, it seems that A is transformed the normal way, and B has the non-normal thing. From these equations, it seems that B behaves normally. B has the conserved currents, and A has the anomalous contribution. So which part of the symmetry is good? Which one is really a subgroup? Well, it's actually given by this. Since, if you remember, we constructed the by integrating the currents which were conserved, and this guarantees that they are topological. So, and also from here, actually, from this perspective, you see what was messing up the situation. It's the transformation of A. So B by itself lives in a perfectly fine world. But if we ignore A, then B transforms as D plus D lambda, and never a problem. But then if A begins transforming, then it can infect B. So we see it from both perspectives that B is the good subgroup, while A is not. So yeah, from either point of view, you can see that U1B is a subgroup of U1A, U1B. Meaning the fusion laws will be the normal law. If I write this, it means it's because the other one is not. The U1A is not a subgroup, and we see it from either perspectives. So here I already explained, and here from this perspective, we see that sometimes it may happen that when we will merge two U1A defects, they will not give another U1A. So let's try to make this more precise. And spoiler, here I want to say that it is a quotient. Okay, let's unpack this. And for that, I will need to go back to a little bit of algebra. Let's try something. I'll try to make a two-column thing. One is wider than the other because there will be more stuff. So in this column, I will explain stuff about H2 of G, point of view 1. G. GA, and here I will explain stuff about H3. So in these two things, I pick G is any group. You write it here. So G is a group, and A is an abelian group. And let's also assume that the group G maybe acts on A. What does it mean? It means that there is an action, so there is a homomorphism from G to the automorphisms of A. Another way of saying it is G here, you can send it to an action which to any element A associates G. acting on A. I would act with a prime. And as we discussed last time, in the homology, there was the possibility of adding this action. So let's just describe what are these actions. And I want to compare these two things, to show that this is something relatively that maybe you know, and this less likely. So H2, it describes group extensions of G by A. So this is actually the standard thing when you study like anomalies and so on. You can say that you have a projective action, you have a projective representation of G, then you can make it into a non-projective representation of the extension of G by some central elements. Yeah. Okay, and now, so the algebraic way of saying those things is that group extensions, they are described by exact sequences. So you have one, the trivial group, and you have your abelian group, the extension, let's call it E, and then G, and then okay, I will not describe just in words. Why is H2 describing the equivalence classes of such things? So there are a lot of things I don't say, but these are group extensions, which means this thing is a group, that's the extension, and it's kind of built out of two ingredients. The two ingredients are G and A. And these two ingredients, well, first of all, G acts on A, so that's one thing, but you need a bit more to define what a group extension is. You need what? An element of that. So, for instance, you can think, if you want an example, is G equals the one that we described at the beginning of the anomaly. G was SO3, A is Z2, and out of SO3 and Z2, you can build the extension, which would be SU2. So sometimes the extension is just direct product, sometimes it's semi-direct product, sometimes it's none of this. And the reason it's qualified by this H2 is because when you have let's call pi, this map, that's a projection. Now you can look for whether there is a section, whether you can invert that thing. So you try to see G as a subgroup of E. So you try to find a morphism here, but this morphism is actually not a group morphism. So there's a problem. So S of G1 times S of G2 is not equal to S of G1, G2. This would be the case if it was a group morphism, if the sequence is split. But here it's not the case, and the mismatch is this omega, G1, G2. So you see it's exactly the same as in the projective representation. Anyway, so why am I saying all of this? I'm saying all of this to say that there is an extension. So that's, again, that's a very familiar thing. That's, say, SU2. And if you want to describe how is SU2 made out of SO3 and Z2, well, it sits here in the middle of an exact sequence. So that's the extension. And those two are the ingredients. Those two are the ingredients. Which are mixed using omega, the element. And now, our situation here is described by H3. I remind you that this kappa belongs to H3. This came from the anomaly polynomial. And it describes, it's very similar to that, that's why I tried to put it on the same column. So it describes what's called cross modules of cross modules K over 8. So in the same way as here, we could build something more complicated out of two groups. we can also build something more complicated out of two groups and given an element of H3. And what is that thing? It's very similar. So still put A, and now you put G and 1. The only difference is that the thing in the middle, it's not just E, it's a thing which has two terms. Okay. So so K and H are just groups, and here there is a map between these two groups. Let's call it T. And there is, again, I'm skipping over all the details, there is a set of equivalence classes of such chains, which are classified by H3. These are the cross modules. Let me not give much more detail. I just want to emphasize the analogy with that. And there are still two ingredients. So that's the extension. But I don't call it the extension because the extension is that. So that thing I will call the cross module. So
K c'est quoi? C'est un groupe.
K is a group and H is a group.
Both are groups.
Yeah, they are just some group morphism, and it sits in this sequence. And I'm looking at the equivalent. I should explain when two such things are equivalent and so on. But then the equivalence classes of such things are classified by that. And but what you should remember, take out of this, that when you have two ingredients like that, you can cook up a more complicated thing out of them in exactly the same way as you can build an extension out of two groups. These are the ingredients, the two ingredients. Eigencopies, these are ingredients which are mixed using omega, the same as here. The difference between the two, they are arrows, so they play very different roles. Here, I mean, I didn't even say what's a short exact sequence, but it means that the image of each arrow, the image of that is the kernel of X and so on. So basically, that thing A is a subgroup of E. That's the crucial thing. This is a subgroup. While this is not a subgroup, this is a quotient. This is kind of E quotiented by A if you want. And the same happens here. That's a subgroup of whatever the structure here is, and that's a quotient. Okay, so let's admit that H3 classifies exactly those things, and therefore, what this transformation law encodes is a certain class of cross modules. And now I want to make it more concrete. I mean, that's probably very abstract. Let me try to make it concrete and describing out of this a certain two group. And so for that, I have to 2 weeks ago, I started drawing. Maybe I should keep that. 2 weeks ago, I started mentioning that all the symmetry defects in when you had a P-form when you had a normal symmetry, the symmetry defects, I said, okay, you can have a dot here, and then you have a bunch of arrows, and these are your symmetries acting on the theory. And these were the zero-form symmetries. Then when we had one-form symmetries, and only that, one way of saying them, and for each picture, we can draw the dual picture. So the dual picture is, this becomes top-dimensional. I make the picture in D equal to 3. So now I have top-dimensional, so D equals 3, so 3 here, and then each zero-form symmetry is a codimension 1 symmetry. So that these white arrows are described by this. These are our usual symmetries. And then we added one-form symmetry. So the one-form symmetry case was when there was no zero form. So there was only one arrow, which is the identity. Identity I don't even draw. If you want, I can draw it in like this. U identity. Identity, so I can draw. And then within identity, I had these double arrows. Let me draw them in orange. So this is the one form symmetry. And these are codimension 1 defects in U, which are codimension 2 in the full T. Right. So these are kind of defects. So we had these two structures and they were not interacting. Either we had a lot of arrows, a lot of white arrows, and then each white arrow, if you want, has its orange arrow, but only the identity. Or we had only one white, and then there were a lot of orange arrows, which are the one from symmetry. And now what I'm claiming is that this is a structure in which these two things are mixed. So let's see how it works. No, we have to write. Okay, I will have to erase that. So let's now define a two category. So I should tell you what are the objects, what are the white arrows, and what are the orange arrows. So there is only one object that I will denote as a dot like here. The different thing. Then what are the one arrows? Well, they can only connect this object to itself. So the one arrows, so on one of the points to itself, these are the zero form symmetries. So this will be the group H here. And now the fun part is the second arrows, the two morphism. So let me not be too precise here. So, and I can draw. So there is only one object, and then there is a bunch of arrows here labeled by the elements of H, H1, H2, and so on. But one of them is the neutral element of H. Let's call it E. E is the neutral element of H. And then what I tell you is that all the arrows that start from E and arrive anywhere are given by K. So the other group, H and K. So now I'm telling you that there is an orange arrow, exactly as many as K. So there is K, maybe it goes back here, maybe one goes here, maybe one goes here. I don't know, some structure. These are the Ks. K1, K2, K3. So right now it's not enough to completely specify it. And then, okay, let me then skip some details. If you're interested, I can tell you, and they will be in the notes. So there are some more conditions in order to specify fully all the arrows. But then I can just tell you what is the most general arrow. The most general orange arrow is something like that. So you have your unique object, dot. You have two white arrows. Okay, so this axiom tells you that whenever you have P here, then you have here I will write the axioms in pictures. So here there is a double, I should draw it as orange. Okay, let me, you prefer orange or double white? Is more visible? No, orange. So here there is a certain K, and where does it arrive? Well, it arrives on some element of H. Which one? Well, T of H. That's the only thing I have in my structure. I have T. So this map T actually tells you only one thing. It tells you where the K arrow ends. K orange arrow ends on which white arrow? But T of H. This is what it tells you. Now, H is a group, so you can compose the white arrows according to the group law. That's quite clear. Now, K is also a group, but how do you compose orange arrows? How do you compose K1 and K2 here? K1 goes here, then K2 goes there. It doesn't match. Oh. It's composed, but how do you compose K2 with K1? It seems not possible, but this is we also mentioned this a few weeks ago, that there is a horizontal composition. So if there is if you have K1 here and K2 here, they both go from E to T of K1 to T of K2 and E. These combined, they can be composed as K1, K2 and E, and here T of K1, K2. And it works because T is a group morphism. So indeed, composing TK1, TK2 gives TK1, TK2, which is T of K1, K2, which indeed is T of K1, K2. So it works. So that's where the law of K.
Sorry, how many objects do you have?
One.
Because in that graph.
I draw them many times because it's easier to draw this than many loops and have things in the loop.
Okay.
The same object.
It is always the same. Okay.
Okay. So you might still be. That's not the most general. I was about to write it, but here I wrote some more explanation of it works. Now let me write the most general arrow. The most general you can obtain by, you can combine here the most generic element. Let's put H, the element of H. There is definitely an arrow that goes from H to H. Which orange arrow? Well, the identity of H. That's an element of K. So that's not an element of K, sorry, because it doesn't start at E, right? K is the set of all arrows which start at E and arrive anywhere. But if H is not E, that's just an arrow. But it's guaranteed to be there because every object has its identity. Do nothing. It's always there. Then I can compose this with E and T of K here. If I compose them, well, what is the result of this times this? Something else. And here you begin to see that K, when you compose, you will see. So the most general element is actually that. H, because H, E, H, and here you have H, E of K, and here you have the composition, let's call it star, 1 H star K. And that's the most generic. That's the most generic situation. But now that we have this, let's go back to physics and let's see where are the symmetry defects. If you remember, I mean, I just erased it, but it's you take the dual picture of everything. So the most generic. So okay, the first thing is that let me summarize the arguments. I said that H3 classifies cross modules. Then out of a cross module, I can construct these two categories here. These two categories is actually a two group. Why? Because all the morphisms are invertible. Easy to check. Like, okay, as an exercise, you can try to find what is the inverse of that one. Good exercise. So all elements are invertible. But that's why it's a bit more than a two category, it's a two group. But now the two group, let's now write it in terms of symmetry defects acting on the quantum field. So the most generic defect is what? When I just take the dual of this. So the dual of this, I have, so this means the theory, the full dimensional theory. The white arrows are codimension 1. So this is kind of a plane like that, which is divided in two by an orange line. This guy, I should write this. This is a bit cumbersome to write, so I will just write H, K. But H, K means that. And then here at the bottom, I have H, and at the top, I have H, T of K. So this is the dual. So this is the most generic. But now, what is the one-form symmetry? Well, first of all, let's get rid of the most generic defect that I can undo that part that I wanted to show you what's the most generic one. But now let's focus on the less generic. Let's assume that H is the identity, or I can compose if you want by I act with H inverse on this. Then what do I get? I get just QFT. And now here I have the identity. I have E. So E I don't draw. It's not a defect. And here I have H comma K for H is trigger. So I will just write K. So what is this? This is a string, if you want, a one-dimensional operator in 3D attached to a surface. Here. So if you remember what we discussed 2 weeks ago, this is a non-genuine operator because it doesn't live by itself. It lives at the end of a one higher dimensional thing. This is a non-genuine of codimension 2. But now, what is the one-form symmetry? These are the genuine defects. So what are the genuine defects? What is the characteristic of the K's which are genuine? An easy question. Yeah. If T of K is also the identity, now K lives happily without any attached to any, right? So what is the set of K such that T of K is the identity? It's the kernel of K, kernel of T. Right? So the kernel of this map, this is the one-form symmetry. But here you have a short exact sequence. So what is the kernel of T? Is this guy. So we have just obtained that. Where is the edge? So this is the one-form symmetry. A is the one-form symmetry. And I wrote it, and so it's called A, so it's abelian. Makes sense, right? The one-form symmetry has to be abelian. The full thing, of course, is not abelian. In general, there's very complicated rules. But what is clear is that the kernel of K is abelian. And now, what is the? So we have found the one-form symmetry. So one-form symmetry. These are the genuine operators of codimension 2. And so this is the kernel of T. Now, what is the zero-form symmetry? Again, 2 weeks ago, I gave a recipe to find the symmetry given all the defects. You remember, the notion was that of screening. You see, T of K, for instance, it's not a zero-form symmetry defect because it can be screened by K. So those which cannot be screened, so what are all the white surfaces which cannot end on any orange thing? Well, you should just kill all of those which can end, and what remains is the rest. So the zero-form symmetry is all of H, but where you have removed the kernel of T, is the co-kernel. I just write this is the co-kernel of T, which is the image of T. It's H modulo by the image. Is it clear? This? Yeah, it is. So those guys, in picture, those guys are just lying like this. The kernel of T I call A, so they are labeled by A in A. And those guys are exactly the white surfaces which cannot end. So they are exactly labeled by this, by G. So we have recovered exactly what we want. So there is two categories. And the arrows in these two categories, they are more general than A or G. You see the arrows, they are given by this K and H, which are much bigger. But this is in the same way as when you have a group extension, this group is much bigger than just G plus A. It's kind of a product. So here the same. The most generic element is this, which I denoted by H comma K. It's kind of a product. But then out of it, you can identify two sub-objects, or sub-things. One is a subgroup, is a one-form symmetry. One is a quotient. Here it's a quotient. So that's a zero-form symmetry. Yeah, and this is why it's called a subgroup. And now, if we go back to this, because this is not a subgroup, it might happen that you combine two elements of G, and you don't, two elements that you think are elements of G, and when you take the product, the element is actually not in G. You have maybe a phase. So this is, if you take this example, you work in SU2, but you forgot that it's SU2, so you think it's SO3. We do a pi rotation, and then again a pi rotation. So you think, certainly I'm doing 2 pi, so I'm back at the identity. But no, if there was an extension, maybe you're at the non-trivial element here. So you do pi plus pi, do pi plus pi. You think you get 2 pi, which is 0, but actually, no. You get the Z2 element. So the same happens here. The same happens here. You are, but it happens with 3 elements here, and you can have this kind of diagram. Okay, so these are various planes intersecting. Let's call this one G, H, K, and then here, for instance, they merge. So this is GH. Over here, it's HK, and then over here, it's GHK. And then there is a point here in the middle where they all meet. From there, you can convince yourself that there is a string which emanates, which is given by some elements of A, so some A like this. Which one? Well, quite clear. It will be classified by the extension, so that will be A will be the omega of these 3. So that's, well, I have not completely proven this, but I've made the analogy with that, and you can trust me that this is the same thing. So what it means is, but it's now in equation or in drawings, I erased, but you know the background gauge transformation. Then let me just write again what was the background gauge transformation. There was A doing nothing special, but B was doing nothing special plus kappa A lambda A dA. There was this thing, this term. So this is exactly what's happening. If you think that G, so the white thing, if you think that the white thing are a symmetry in themselves, then you find an inconsistency. Why? Because let's say that you start with a particular background of A, so you have a particular symmetry background, which will be actually something like this plane that we had at the beginning. And then let's say that you activate a lambda which changes the position of that. Remember that lambda is adding theta function which move defects. And if you move it in such a way that you arrive at the other configurations, as we drew at the beginning, and so that is here, but then that guy here. Now take this picture that we drew at the very beginning and rectify it, like put this horizontal and so on, and check that this is the same as this picture. Right. If you cut this here, you find the first tree. If you cut it behind, you find the other tree. In between, when you have evolved from the first tree to the second tree, this guy has emerged. And this is how the anomaly is there. So which means that situation with these intersecting planes would be inconsistent without the one-form symmetry. So the zero-form symmetry is not a subgroup. The orange thing are perfectly fine by themselves. Okay. Any questions on this? So that answers partly the question that I asked at the beginning. We have gauged U1C, and now we have emerged with a new symmetry structure, which involves two groups, which mix in a kind of an extension, but it's not the standard extension. It's an extension of a 0 with a 1 form, and the way to describe this is either this cross module, or what I just described here, a higher group. This is the way, and this is actually the most general way that the 0 and the 1 form symmetry can mix together. Then, of course, this game you can play with 0 and 2, and 1 and 2, and 0 and 2, and so on. You see the difference. Yeah. So two group is with some hand waving, but it's a 2 category where all the arrows are invertible. So in the same way as this I said I think last time, a group is just a category where all the arrows are invertible, and with one object. So group, you can see as a category with one object, and all arrows are invertible. And this is quite clear. One object, and then you can compose, because it's all invertible, you can always invert. And when you compose arrows, it's part of the axioms of category that is associated. Now the generalization is you can put n here, and then you put n here. So if it's 2, then it's just 2 categories. So you have 2 kind of arrows. There are some subtleties, but that's the thing. And you see, we were led to this. We did not say one day, oh, let's take some very fancy algebraic structure and let's try to build a theory with that. We were forced to do it by just the anomaly and gauging. If we accept the anomaly and we accept gauging, then we have to accept this. And this takes place in the most standard QFTs that we have, like again, some QED-like theory. I think I have 10 minutes more, so I will. In 10 minutes, I will do the other question. But first, I need to make some comments about applications of that. So the two group or the cross module is all the same. I denoted it as U1A times with a kappa U1C, U1B, sorry. One here. So this kappa is a structure constant, and as I said, it's quantized. It's in Z. So it cannot be renormalized. It cannot, if you run the RG flow, it cannot change value unless it jumps. Then you have to explain why. Therefore, this is quite a solid structure. And if it can constrain. Okay, I don't have time to explain, but it can constrain model building. One way of seeing this is because of what I said in the theory. I said that the zero form symmetry cannot live by itself. If you have the zero form, because of this diagram, you need to have the 1 form. Which means if you have an RG flow along which you have breaking of those symmetries. At some energy, maybe you have the breaking of the zero form symmetry. At some energy, you have the breaking of the 1 form symmetry. So you have your RG flow. Let's say this is an emergent symmetry. So deep in the IR, you have the 2 groups. So you have A and B, these 2 things. And then there is the breaking at some scale of A and the breaking at some scale of B. Can you have the breaking of B to be here and the breaking of A to be here? If this is the case, then here you would have only A. This would be fine. It's the other way around. Here you would have only A. But we say A is inconsistent by itself. It needs B to live. So this is impossible. So you cannot break A before you break B, or B before you break A, depending on which thing. So that kind of argument constrains the RG. That's one possible concrete application of this. And the anomaly has to be matched and so on. So this we discussed a bit. Okay, so I've been quite I hope at least you like that it was listed here. Let me just say now 2 words about the other side of the question. It was my third class about the non-invertible symmetry. So we have seen that gauging so remember the anomaly polynomial, we had K, AAA, AAC, ACC, and CCC. This one has to be 0, otherwise you cannot gauge. This one can be non-zero, it's just tooth anomaly, let's ignore it. This one we just work out. It creates the 2-group structure. So we work it out. This one we understand is tooth anomaly, so we are left with this one. That I said is the ABJ anomaly. And so one example where, yes, so let me just write. So the equation is actually where all of this field originates, I guess, in the history of physics. If we go back on the timeline, I don't remember which year this is, but ABJ. So this is the ABJ equation. You have, so for instance, you take QD, and then this is the axial current, the one with gamma 5, that rotates the fermions of different chiralities in opposite ways. And then you find that the conservation equation, the would-be conservation, gives that. And here you have twice the gauge field now, twice the gauge field strength, because it's ACC, so you have ACC. And so question, can you play the same game as what we've done before? So just before we had A and C, and because we had A and C, there was a way to cook up this background gauge transformation, which was able to absorb the anomaly. Now with this is not possible. No such game will solve the situation. So yeah, the current seems to be hopelessly not conserved, and therefore the axial anomaly, the axial symmetry is broken by a quantum anomaly and so typically what you read is that the axial symmetry is a symmetry of the classical theory, of the classical Lagrangian, but then quantum mechanical effects, which you can track to the measure of the fermions and so on, break it, and that's it, it's broken. It's a symmetry of the classical view, but not of the quantum. Now, this is the classical take on that. The modern take on that question is that it's not this. The modern answer is U1A is a symmetry. It is a symmetry of the full quantum theory, no problem. So how do we reconcile these two statements? Well, it is a symmetry, but slightly unusual one in the sense that it is non-invertible. So actually, you see here, there was it's always this game where we have a definition, and then at the beginning there were many things. There were codimension 1 defects, fusion should obey the group law, all invertible, and so on. And then we dropped codimension 1, then we dropped group. Now the last thing to drop is invertible, and then we have nothing left. And that's the idea. So it is an invertible, but a non-invertible. It is a symmetry, but a non-invertible one. And okay, so in 4 minutes, the idea is, okay, I will just explain the idea without writing equations. The idea is the following. So you try to make this into a, we need to find a topological defect, right? That's the rule of the game. So we pick a surface, sigma 3, and then we try to integrate over sigma 3. We try to integrate star of J1. That would be, so if we had exponential of I alpha times this, that would be our symmetry defect. Of course, for this to be topological, we need d star j to be 0. It's non-zero. So, okay. So now let's try to fix it. First, that, and then, okay, you try to fix it, so you remove something whose derivative will be that. So something like 1 over squared C1 with BC1. So now you say, now it is invertible. It is topological because d of all of this is 0, right? Except that, what's the problem? It's not gauge invariant because this is a Chern-Simons action. What is the level? It's alpha. Alpha is an angle, it's anything. It is, and it has to be quantized. So actually, the only way that this can be quantized is if alpha is a 2 pi or something, you can fix, and then it's exactly when the symmetry defect is triggered. So the only symmetry defect you can generalize is the 2 pi one, which is not. So you're completely doomed with that. And okay, now the solution to this is to add is to replace this term by this is again kind of an anomaly, and the idea is to repeat what we've done before, is to add some edge modes from one more dimension here that could be absorbed. And an equivalent way of saying this is to add this and a bunch of fields which are defined only on the defect. So the defect now carries some fields which do not extend in the bulk. They are localized on the defect, but they have some action and so on. So I could write, just write this. So this term, which is the ill-defined term, I replace by the integral over sigma 3 of, let me write and explain, n over 4 pi gamma 1 gamma 1. So here I replace c by gamma into Greek, but now there's n here. And I will assume that alpha is 2 pi over n. N is an integer. I take an angle which is a rational angle, rational 2 pi. 2 pi divided by 10, and now I here. So now this is Chern-Simons, but with a quantized term, so that's fine. And I add a topological term, which is 1 over 2 pi gamma 1 with b. And now what you can check is that if naively you integrate out, that quadratic action in gamma, it has term n here, and if you integrate it out, you find that it fixes gamma to be, so you don't integrate, you find the equation of motion for gamma, it fixes gamma to be c divided by n, and then if you plug this back in, you recover this. Except that here, if you write it in this form, then well, there will be a way to make the operator well defined, and at the expense of making it non-invertible. And the general idea for making non-invertible defects is to identify a duality of the theory. So if you have a theory T, then if you assume that this theory is equivalent to the same theory but modeled out by some group action, so there is a gauging which reproduces the same theory. So this, we also saw examples of this. This is, for instance, electric magnetic. It's not exactly that. But there is electric magnetic duality in Maxwell. There is well, maybe the most simplest one is the two-dimension in the Cramer-Zdanyi duality. Okay, if you have a duality, basically the idea is you can engineer a defect which has T on one side, then the gauge thing here, and that's basically the idea. And now when you compose two things like that, so if this you call D, this is the defect D, then the typical thing that you read is that D, when you compose it with what would be its inverse, so you minus I and you think that you will cancel everything, then what you get is not 1, not the identity, not nothing, but something called C, which is called a condensation defect. And I can just draw a picture of what this is. So here you have this, you have T, and then you put the inverse. So you kind of reflect this picture. So you have again D here, and then you're back at T. And now the question is, what is this sandwich here? And because you have T divided by G over here, you have gauge in a very small region. So if you push this all together, you get C. And what is C? Well, as we said, gauging is like inserting this foam of defects. So over here, you have this foam of defect, the thing that you have gauged, and now all of this is stuck here. We have something like that. This is called condensation defect. It looks like it's three-dimensional, but actually it's only two-dimensional, which means the one-dimensional operators, the local operators, they will be able to cross. It's 4 rows to them, but then the line operators and so on, they will be affected. So this is not the identity operator. So D times D is not the identity, and there is actually nothing that you can add to this thing which can make it non-trivial. So, okay, so this was very, very brief at the end. Let me summarize now very briefly. The question of today, I think we more or less answered the first part. If you gauge with this kind of anomaly, you get these higher groups, which are still grouped. Everything is invertible, but the low part, the high dimensional part, cannot live by itself. So you need to add more. And then if you consider the other anomaly, it forces also to drop the assumption that it is invertible. And so the full picture is that, and that's the answer to the question at the very, very beginning, what is the structure that replaces group? Well, it's some kind of category, well, the set of all these defects and how they interact together. And then maybe you should ask someone else to give a lecture on how to apply this to model building and particle physics and string theory and so on. And, yeah, I'll stop here. Thank you. Any question? At the end was really interesting.
So if no questions, thank you, Antoine, for the great course.
We stay until the end. And yeah, if you want to discuss, also the idea of giving this course was to trigger some discussions and so on. So if you're interested in this kind of topics,